Okay. All right. So how's everybody doing? Okay. Yeah. Monday. We're getting there. Um, Anybody know when the end of the semester is?
And the exam will be on 9th of May.
9th of May?
Yes.
Okay. Okay. Usually what I do is try to have the exam like the last day of class instead of waiting till the exam week. Would that work for most of you guys? Yeah, okay. That'd be okay. Because I just like to get it over with, and I don't like to get in the way of your other exams. So probably a lot tougher than mine. Okay, so we'll get there. So if it's May 9th, so the last week of class will be like that last week of April, first week of May, somewhere in there. So we'll figure it out as we get closer. But like I said, it'll be kind of comprehensive or cumulative or whatever you want to call it. But it'll also be qualitative. So people, so Domi, and maybe some of you guys that had me a couple of years ago, you don't know that. So my exam is mainly just qualitative. So it'll just be answering, just be asking you questions about basic concepts that we've covered. Okay, so it'll be like fill in the blank or explain something in a couple sentences or true or false or multiple choice or something like that. Okay. So it's nothing to get stressed out or worked up about. It'll be fun, and all you guys are fine as far as your grade goes. So, okay. All right. And I guess I haven't looked yet, but I guess I'll put another homework in the Dropbox soon. But like I said, any of these homeworks now, you can just wait till the end to turn in if you don't have time. But if you want to keep up with the lectures, I recommend at least giving an attempt to them. Okay, so we've been talking about second quantization, right? And last time and the time before, we worked out the quantization, or basically solving for the eigenenergies of a system of degenerate electrons. So these are electrons identical, they're obviously identical, and trying to solve for the energy eigenvalues of that system. Okay, so that's kind of the prototypical example of a system of fermions. And those types of systems you'll see not only in condensed matter, but if you went on and studied astrophysics, something like that, that type of system comes in if you study like white dwarfs or neutron stars. So the fact that you have this degenerate Fermi gas basically holds up a white star against its gravitational pull, right? So there's other applications besides condensed matter. Anyways, okay, so what I want to do today is talk about how we can use this second quantization way of to quantize the electromagnetic field. Okay, so I have to warn you that there's going to be a good deal of electros, E&M in this lecture. So if you have your air sickness bag with you, you might want to pull it out now. I'm just kidding. It's so I'll kind of what I'll do is just kind of go through E&M, in a nutshell, and talk about how we can use our basically. So the first half or 3/4 of this is going to be classical physics, really, and then we'll quantize the theory using our second quantization. Okay. So basically, what we want to do is start with Maxwell's equations. Okay, so we want to start with 4 Maxwell equations, and we're going to work in a simple case where we have an absence of charges, okay, or currents. So we're going to have basically a box of photons, okay, with nothing else, or just a box of light, if you will, or an electromagnetic field. Okay. So this is going to be tricky, right? Anytime you deal with Maxwell's equations, it's not never really straightforward, but we'll work out the theory and like in a classical way, and then it'll be hopefully obvious how we quantize this, and then we'll talk about how you do it in the case of second quantization or using many-body formalism. Okay, one thing that we know, and we don't have the tools yet to prove, is that the particles that we're talking about, photons, are spin 1. So they're integer spin, so they're going to obey Bose-Einstein statistics. And I say that we don't have the tools to prove it because you need to consider a fully relativistic theory in order to prove or show that photons are spin 1. Okay, and I don't think you can even do it with relativistic quantum mechanics. I think you have to go up to quantum field theory to prove this. But we'll work under that assumption. Okay, so this is something that we're just going to take as an empirical fact. Okay, and these fields, when we get to the point of quantizing, they're non-interacting fields, right? Photons, light doesn't interact with itself, and the only thing that would interact with are charged particles like electrons, right? So we're considering a simple case where we don't have any interactions, right? If you want to include interactions, then you have to, then that's called quantum electrodynamics. And if you want to study that, you need to take QFT. Okay, so it's always my commercial to take QFT. Okay, so let's start by talking about Maxwell's equations in free space. Okay, and so we're going to start, like I said, with the classical theory. Okay, so let me write down Maxwell's equations in the absence of charges and currents. And I've long forgotten the names of these equations, so I'm just going to refer to them as A, B, and C, D. Okay, but these are Maxwell's equations, right? And these are the equations that we need to solve in order to, be able to write down solutions for the electric and magnetic fields, right? For whatever phenomenology we want to talk about, whether it be, all those contrived things that you learn about in Jackson, okay? Like, light in a conducting sphere or something like that. Anyways, so these are the equations that we want to solve. All right? And to be honest, I mean, Maxwell's equations are awesome. I mean, they're beautiful that you can write, electromagnetism in 4 equations like that. But when you're taking E&M and you're taking Jackson, you don't really appreciate them. You get bogged down in trying to solve these goddamn problems, But I used to have a professor that he didn't teach our E&M class, but we would go to him with questions. And every question, it didn't matter, it'd be some some Jackson problem with a coaxial cable or something, and you had to, electric field or something. And you would just be like, oh my God, where do I even start? And this professor that I would go to, he'd always be like, okay, let's start by writing down Maxwell's equations. And he would write down, and then, and everything would just kind of beautiful, fall out beautifully. I've never gotten to that point, so don't come to me with E&M questions. But they are useful. So I think as you go along in your career, especially, I mean, in my research, I never deal with Maxwell's equations. You know what I mean? But for condensed matter physicists or people doing experimental physics, they're probably more useful. Okay, so you probably get a better appreciation for them. In my field, in quantum field theory, you see, if you take quantum field theory, you'll see that you can condense these 4 equations down to 2, and then after that, once you quantize it, you don't give a damn about Maxwell's equations. Okay, you just worry about photons and how they interact. Anyways, okay, so the typical approach to solving these equations, right, or one typical approach, is to postulate the existence of potentials, right? So we have a scalar potential for the electric field, and we define a vector potential for the magnetic field. Okay? So we define both of those. We define E and B in terms of phi and A. If we don't have any charged particles around, right, that means that the scalar potential is automatically 0, right? When there's no charges present, okay? And so what we're going to work with mainly is this magnetic field, right? But we know that a magnetic field generates an electric field, and so you get your photons or electromagnetic waves. Okay, so we're going to define our magnetic field in terms of this vector potential, right? And you could see that automatically when I write this down, if I go back up here and look at B, I know that the divergence of any curl is 0. Okay, so we've already checked off one of these equations as satisfied, check, okay? And if you've been through E&M, you know that when you're working with electromagnetic field, you always have a freedom in the gauge that you choose, right? You have I don't know how to really say it, but you have what's it called? I can't remember. But so you have a freedom in which gauge you work in, right? And so the one that's most commonly used is called Coulomb gauge, right? And that's where you enforce that the divergence of this vector potential is 0, right? And if that's the case, when you plug in the magnetic field, you find that the electric field can be written in terms of the vector potential in terms of just a derivative, time derivative. Okay, so the oscillating vector potential or the oscillating magnetic field gives us an electric field, right? Okay, and then so with this and the prior definition for B, you can plug it into equations A and C, the first and the third equation. The first is del dot E, right? So del dot E, I plug in my expression for E in terms of this derivative, use the fact that these two derivatives commute, and then I have the time derivative of del dot A, but del dot A is 0 in the Coulomb potential, or the Coulomb gauge. So the first equation is satisfied, and then you can plug in the second. For the second equation, I've got a curl of E plus the time derivative of B. And if you plug that stuff in, and again, use the fact that the time derivative and the spatial derivative commute, you see that the two pieces just cancel each other off. Okay, so now we've satisfied, if I go back up here, we've satisfied all the first three equations. Okay, so what about this fourth guy? Okay, well, that's going to give us the dynamics of our field, right? Right. So what we've done is basically taken our problem and reduced it from one where you're trying to solve for the electric and magnetic fields and trying to a situation where we're just trying to solve for this vector potential, because once we have the vector potential, then we can compute what E and B are. Okay, so what about that last equation? Well, the last equation is curl of B and the time derivative of the electric field. All right, so I plug in what B is, it's a curl of A. Plug in what E is, it's a time derivative of A. Right, and I use some identities here. The curl of the curl gives me this thing, and time derivative. So I have two time derivatives, and I notice I'm missing a factor, or a 2 here, but it's second order derivative, right? And so it leaves me with this, but this first term vanishes, right, because I'm in the Coulomb gauge. So in the end, I get an equation for my vector potential that looks like this. Okay, so we've taken, just to summarize, we've taken Maxwell's 4 equations. We've used our freedom in the choice of our gauge to basically eliminate those top 3 equations and just work with one equation, right? And we get one equation for the vector potential, which looks like a what type of equation? A what? It rhymes with the Schmave equation. And it starts with W. It's a wave equation, right? This is just a basic wave equation. Second order spatial derivative and a second order time derivative. Okay, so it's a wave equation. Okay, and the wave has a magical speed of c, right? Which is a constant that we put in back when we were deriving the equations, Maxwell's equation. Okay, so if it's a plane wave equation, then we know how to solve it, right? it's second order in space and second order in time, so we have to make sure that we, in our solutions, we include both space and time pieces, right? But the solution you can show looks something like this. Okay, so this is my full wave vector, vector potential, right? And I'm writing it in terms of some coefficient, okay, that depends on the wave number. Don't worry about that right now. But the spatial and time dependencies come in as oscillating exponentials, right? And you can show that if I take this and I plug it into this equation, it'll be satisfied, okay? And here, omega, I've defined omega, but omega is just k times c, basically, the magnitude of k. So we've got a solution, right? And we can ask, can the Coulomb gauge, can it tell us anything? Right. So we have a solution, and we'll go back and figure, what to do with it. But the first thing you ask is, say, okay, well, I have this condition that del dot A is equal to 0. So what does that tell me about A itself? And if you plug in A, you find that this condition implies that the dot product between A and K, right? Remember, K is pointing in the direction of the propagation, right, of the wave, right? So it's telling me that these coefficients are they're orthogonal to the direction of motion, right? And if we're working in 3 dimensions, that means that we basically got 2 eigenvectors that we can choose, right, in that plane, okay? So it's telling us that A is perpendicular to the direction of propagation, okay? And so we can use that to our advantage, all right? So what we can do is now, like I said, we have 2 basically eigenvectors that we can use to span that 2-dimensional space, right? And so I can write my solution, my vector potential, in terms of a linear combination, right? So this is just like breaking, we would have some eigenvector that's perpendicular, or some vector that's perpendicular to the direction of propagation, and I'm just breaking that vector down into 2 eigenvectors. Okay, so there's a sum here, but it's just a sum over 2 eigenvectors, right? So these are like our unit vectors. This is like x hat and y hat if we were just working in it with a regular vector. And I don't know why, but I use a vector notation on this A here all the way through the notes, and it's not a vector. Okay, so what I've done is I've taken this vector and I've written it in terms of unit vectors and some coefficients. Okay, so when you go back through these notes, just make sure you understand that this is not really a vector. Okay, and I don't know why I did that, but I did it all the way through the notes. Okay, so these guys are just unit vectors, right? And they correspond to 2 values of lambda, where lambda is basically the spin, or the direct, or the point. How do I want to say it? Well, let's just say it's 2 values of lambda. Okay, so we have two different directions, right? 2 perpendicular directions that are perpendicular to k. All right, so that means that I can write this coefficient, right, in terms of 2 pieces. Okay, and this comes from the fact that we want this field to be real. Okay, we want the vector potential to be real because we want the magnetic field that we get from it to also be real. Okay, so what I do is I'm imposing that this field I can write in terms of 2 terms. One that would basically correspond to a left propagating wave, and the other that would correspond to a right propagating wave, right? But you can see that this thing is real, okay? So if I take the star of this, this becomes a star, this becomes a plus, this becomes unstarred, and this becomes a minus. And we are summing over, so this is a sum not only in the direction, so the lambdas, but it's also a sum over the possible values of K. Okay, so we're rewriting this thing as a sum, and we all know that, space is continuous, especially, when you're dealing with classical physics, right? So this would usually be an integral, right? But I have in mind that we're going to be working in a quantum system, and so I wanted to simplify it and just deal with it in the big box approximation, right? So I can rewrite that integral, which would be there over K in terms of a sum. Okay. And just to note, with that in mind, that we're going to be working in quantum theory, when we go on and compute the energy, you're going to see that we're going to want to take this field and basically square it. Okay, so when we square it in a classical theory, these guys would commute with each other, A and A star. Right? You could A times A star would be the same thing as A star times A, right? Yeah.
I'm a bit lost. Why would it normally be an integral? Because I thought that we were working with 2 unit vectors. That's why we.
Yeah, the 2 unit vectors are the spin direction, right? But we're integrating over all. When we wrote it back here.
Sorry, I got lost.
Yeah, so when we wrote it here, see, I think I'm missing this one. I think because this is, let's see. Yeah, I think I lost myself too.
And one other question. So I was also going to ask about that earlier, but
Mm-hmm.
past. So the divergence of A that says, I'm not exactly seeing how we got to the next step.
Here?
The above one. Yeah, sorry, where you were.
Right here.
Yeah.
Yeah, so if you take your expression for A, this guy, right here, and you take the divergence, it's going to pull down this factor of IK.
But we're taking the divergence with respect to X or K?
X.
Okay.
That's the way we defined the Coulomb gauge.
Okay.
Yeah.
We'll have to review those rules.
Yeah, so we haven't, here we're still working in position space. I think what I'm doing here.
That would just be like the lambda would.
Yeah, the lambda would be the unit vectors.
I guess you could integrate it. It just seemed like then you're integrating over a sum of different directions, which could be reduced to just adding up 2.
Yeah. So these. Yeah, it gets a little confusing because I'm taking the field, I'm breaking it down in terms of these pieces that are parallel to these unit vectors. And then I'm taking this piece, right, and breaking it down further. That's what this term here is. And I think when I do this, usually an integral in K would come in from taking, if you're using a Fourier transform. So I have a feeling that's probably what's going on behind the scenes, right? But I don't remember the details, to be honest with you. I'll have to go back and look.
I thought you meant integral over lambda.
No. It's a discrete sum over lambda. But we're integrating over K.
Okay, never mind.
Because you have to sum over all.
Sorry,
Okay, sorry. All right. Okay, good. Is everybody else clear? Okay, so it gets a little confusing because it's like, the old peeling back the layers of the onion, right? We start with the vector potential. And so we've shown that it's perpendicular to the direction of propagation, right? And that is a plane. So I'm writing the plane in terms of eigenvectors, right? So I write that field in terms of components along those eigenvectors, and those components themselves satisfy our wave equation. Okay, satisfy this guy. So individually, you can show that the different components satisfy, right? And we want these coefficients to be real, right? So we write it like this. Okay, so we have the original expression, but we also add on the starred expression. Okay, or the Hermitian or the complex conjugated form. Okay, and we're working in the big box approximation, so that's why this integral that would come in from taking a Fourier transform is written as a sum. Okay, and like I was saying that when we compute, so we're going to want to compute the energy of our field, our electromagnetic field, and that involves taking basically absolute value squared. And so we have to be careful, when we're keeping in mind that we're working in a quantum theory, because these guys won't necessarily commute, right? So we'll see that they kind of correspond to annihilation and creation operators, or that's how we're going to basically quantize the theory, is to promote these coefficients to operators. Okay. All right. So, and it turns out that it's a lot easier to, instead of using linear polarization, so instead of using I don't remember what the notation is, but instead of just using linear polarizations, one that points up and one that points this way, we're going to use circular polarizations. Okay, so we'll have a left and a right polarization, right? And it's an equivalent way of describing the physics, but it turns out to be a little easier because you can define those the unit vectors in that basis, the circular polarized basis, in terms of the the x and y, say, type of basis. Okay, and again, so here instead of 1 and 2, which would have been our the axes are our eigenvectors in that plane, lambda is going to be either plus or minus. And I don't remember. I think plus is right-handed and maybe minus is left-handed. I can't remember, but it doesn't matter. Okay. All right, so we can write down with this definition. You can write down a couple of identities that are really helpful, and this is the reason that you write it in terms of circular polarization. One is that when you take the dot product of some unit vector starred, right? So these guys can, when you write them in circular polarizations, they can be they are complex, right? So you take the dot product of these two guys, and it gives you a delta function. Okay, so notice that I'm taking the dot product and I have the same k here. All right, so it gives me a delta function in the polarizations, plus or minus, depending on the sign of your momentum vector. And the cross product between these two guys also gives me a delta function, but it gives me, it depends on the factor of lambda, so either plus or minus. Okay. All right, so finally you can get down to the nitty gritty and take your solution for A and plug it into the expression for E, right? Because that's what we want. We want expressions for the electric and magnetic fields. And that's where it gets a little tricky. So I'm going to take what we had for E, which was just the time derivative of A, and plug in our solution of A. So all this stuff back here that we had, all right, so with these coefficients, all right, and if I plug that in and take time derivatives, so this is that stuff plugged in, and so this stuff plugged in. I take time derivatives. It's going to pull down factors of omega or I omega k, right? And that is just a constant, so I can pull it out in front, and I get this kind of prefactor. I still have my sum, right, over the polarizations, and then I have the two pieces from the original wave, right? So that's the electric field. Right, you can do the same thing for the magnetic field. It's a little more complicated because you have to take the curl. So I'm going to skip. I'm going to skip that calculation. Right, you end up basically with the same thing we had before, but you end up with these factors of the wave vector being crossed into these polarization vectors. Okay, and I'll show you what B looks like in just a second. Okay, so what we're interested in, we want to quantize this theory, right? And the way we're going to quantize it is to basically write down the Hamiltonian and promote it to an operator, right? And so what we need to do is be able to compute the energy of this electromagnetic field. And if you go back and look at Jackson, you'll see that the energy of this field is typically written as a volume integral of E squared plus B squared. Okay, so this is the definition of the energy or the energy density of your electromagnetic field, right? And it's a volume integral where typically you're taking the volume of all space, but here we're working in big box approximation, and so we're going to have periodic boundary conditions. Okay, and those periodic boundary conditions result in just the normal type of quantization relationships between the wave vector and some integer numbers, right? So this is like a particle in a box, right? But it's the same thing as one of those contrived examples in Jackson, which is an electromagnetic field inside a cavity with conducting walls. Okay, I don't know when that comes into play or where that comes up. Yeah.
Was there a constant missing in that electric energy density?
It depends on which. There are. I can't remember what the name of. There's a special. Where you basically said epsilon and mu is to 1.
Oh, okay.
Yeah, I can't remember what it's called.
You said C to 1. And, yeah. Okay.
Yeah. It's a special. Yeah. The name escapes me, but there are special units where you set mu and epsilon to 1.
Okay.
Yeah. So that's whatever the name of that formula or that
it's escaping me.
Yeah. It's weird. It's what especially coming from Griffiths and stuff like that, and probably I'm sure that Jackson has epsilon and mu's in there wherever they go, right? But in quantum, we try to get rid of as many constants as we can, so we work in units where everything's 1. Right? Okay. So we have boundary conditions. Okay, so that's going to mean that our K is basically quantized, right? So this is the case in quantum mechanics, but so far we're still working in classical physics, but because we have a finite space, we're going to have these boundary conditions, which basically quantize our wave number, right? So it's basically setting up standing waves, right? If you're in E&M right now, okay. All right. So what we want to do is compute this energy density, right? So we need to write down the electric field, right? And so I have this, and what am I doing here? I am, I guess these are, I'm writing down the electric field. Oh, and then I'm writing down, I think the notation's screwed up here, but I'm writing down the electric field in terms of these vectors, right? And then I'm reducing these vectors using our the sum over these unit vectors. Okay. But anyways, so we have the electric field. We can take the complex conjugate, and now we have to square it, right? And you notice that when I take the complex conjugate, I put primes here, right? So this is just to be safe, because in general, these are expansions, they're linear superpositions, right? So there's going to be cross terms between the two. And if you had written, use the same dummy indices as you did here, you're going to miss those cross terms. Okay, so you have to be as general as possible, right? So as if I'm summing over these dummy indices, I want to make them different. Okay. Anyway, so you take this, you multiply by that, you keep track of the order of A and A star, right? Because they're going to become operators, right? And I'll give you E squared. It's a mess, right? So it's got these 4 terms, right? And they're all being summed over. But the thing that you notice is that you have a couple things that are going to help you. One is that you got the dot product between these two guys, right? The other is that you have in each term you have some factor that goes like e to the minus ik dot x, right? Being integrated over all the volume of space, and that's nothing but a Dirac delta function, right? Our old friend. And so you can write it like this. So I'm writing it in terms of Kronecker delta function because we're using this big box approximation. And so what I have to do is if I'd write it like that, I have to include this factor of v, right, to give it the correct units, right? So anyway, so usually this would just be a Dirac delta function, but I'm writing it in terms of a Kronecker delta function, and then I included this factor of v. Anyway, so what this does is it sets k to either plus or minus k prime, or vice versa, k prime to plus or minus k. And then once you do that, then you have this dot product of E with sub k dotted into E sub plus or minus k now, right? And so you can use the identity that we had before, which is it basically just gives you a delta function in the polarizations. All right? And so when you do that, you can simplify a lot of stuff and you get down to this, right? So I'm keeping the order of these guys straight. So I have two cross terms, right? And so here's my two cross terms, and then I have the two terms that go like A and A star. All right, so you do the same thing for the magnetic field. And like I said, the magnetic field is a little more complicated to compute. But what you find is that when you compute B squared, you basically get back the same thing that you got for the electric field, right? Except for some signs, right? So in front of these A squared and A star squared terms, you have minus signs, right? So when I take E squared plus B squared, these terms are going to cancel each other out. Right, and I get a factor of 2 on these guys, right, the cross terms. So when I put everything together, I get something that looks like this in terms of our coefficients, okay? So this would be our starting point for a quantum theory, okay? So we would have this is basically our Hamiltonian, our Hamiltonian density, right? And we see that it goes like omega squared, and we have these operators, A and A star. Okay, so what we want to do is take our Hamiltonian and promote it to an operator, right? And for quantum theory, right? And what we want to do is we're going to work in second quantization, right? Because we're going to have a system of many photons, right? We're dealing with particles now. Okay, so we're moving away from this wave interpretation of the electromagnetic field and talk about it in terms of photons. So there's going to be a lot of photons, and we don't want to have to try to keep track of each one, right? So we want to use our second quantization, okay? And the way we're going to do that, so we know that in second quantization, we write down annihilation and creation operators that annihilate or create particles, right? In this case, we're going to have like a creation operator that looks like this. So it's going to create a particle with momentum k and spin lambda, right? And likewise, we're going to have an annihilation operator that annihilates a particle with momentum k and spin lambda. Okay? And so the energy of an individual photon, we know from Einstein, I think, was the first one wrote it down, or Planck, I can't remember. But it's energy of a photon is h bar omega, right? Or in terms of the wave vector, h bar c times k, right? So if we know the energy, right, we can write down our second quantization form of the Hamiltonian, right? It's just going to be the energy of a photon, right? And the energy is going to depend on k, so I'm going to put the subscript k here, times a number operator, right? So the full Hamiltonian, or the full energy of our system, is going to be basically you count up the number of particles that have k and lambda, and you multiply it by their energy. Right, so we're writing our Hamiltonian just like we did for the fermions. Remember there we had p squared over 2m for the kinetic piece times the number operator, right? Here we don't. So here we don't have the interaction term, so it's a lot simpler. We just have the kinetic term. So this is basically the kinetic energy term of the photons, right? Okay, so we're doing the same thing that we did before. Okay. And again, like we said, photons don't interact, so we don't have these two-body operators that complicate things, right? And so now you come to the point where you say, okay, I've promoted, or I've written down my Hamiltonian in second quantization form. And now I need to impose some symmetry on the system, right? So in the case of fermions, we knew that they were, well, or in the case of electrons, we knew they were fermions, so we imposed anti-commutation relation, right? Here, photons, like I said, we don't have the tools to prove it right now, but we know empirically that photons are integer spin, they're spin 1. So that tells us that we want to impose Bose-Einstein statistics, which corresponds to imposing commutation relations on our annihilation and creation operators. Okay. If you look in Saccharide, there's a kind of a hand-waving way of determining the spin of the photon, if you're interested. But like I said, to prove it, you need to use a fully relativistic quantum theory, in other words, quantum field theory. Okay. Okay, so we're going to impose these commutation relations now, right, on our operators. And so what we want to do is basically make a connection now between our quantum form, right? So we have this guy, right, that we wrote down just using our rules of second quantization, right? But we also have this form back here that we got from the classical theory, right? So here we're going to promote this to a Hamiltonian, and we have to figure out what do we do with these? What do we do with these coefficients? Right? Everything here out in front are just constants. So these are going to be the guys that we have to promote to operators. All right. So let me go back here. So what I want to do to make that connection is look at our second quantization form of or Hamiltonian. Right. So it's a dagger. It's the number operator. Right? I can use a little trick. So I can rewrite this as a dagger A plus a dagger A times 1/2. All right, so that's what I do in this step, going from here to here. Right, so you see the factor of a half. I haven't done anything, right? But now I want to pass this operator, the annihilation operator, through this creation operator, right? And because of the commutation relations, that's going to give me back a dagger plus 1. Okay. And now what I want to do is I want to compare this guy to the form of what I had from the classical theory. I should have just written it down there. But when I compare it, I can see that these guys, these coefficients, are going to correspond to my annihilation and creation operators. Right. So you see, go back here and you see that it has the same form, right? So we can read off basically the relationship between A and A, big A and little a, right? So our coefficient A is going to correspond to our annihilation operator. There's a whole bunch of constants that come from, matching the two. But the important point is that we identify this guy with the annihilation operator, right? And likewise, when we take the Hermitian conjugate, because now we're dealing with operators, right? Hermitian operators. So we have our operators. We have to take complex conjugates, in other words, star, and replace with dagger. Okay. So then we take the dagger of this, and it would give us a creation operator. Okay. And that's it. So we've basically quantized the theory in two different ways, right? We took the classical theory, we worked all the way through it, and got the energy of electromagnetic field. And then we said, okay, to quantize this, we're going to promote, these coefficients to operators, right? And at the same time, we could write down the Hamiltonian in the second quantization way, and then we compare the two and make to identify the coefficients with the creation and annihilation operators. Okay, and so we're basically done, right? But there's one troubling part, and it comes from this fact, or from this part right here, this kind of innocent-looking factor of 1, right? And it's a constant, right? So one is, doesn't depend on k, right? And you see here what I'm doing is I'm summing over all values of k, okay? And now what happens when I go to the continuum limit, right? If I go to a continuum limit, this sum over k becomes an integral over k. And it's an integral over all space, right? And an integral over all space is going to give me an infinity. right? So this one right here, even though it looks harmless, is just a little one sitting out here by himself, gives us an infinity, right? So it's basically, there's no, and what you see from the quantum theory is that there's no factors of A and A dagger attached to it, right? So it's not like it's associated with any particular photons, right? It's associated with all of them, right? And so it's basically the fact that you have no A and A dagger, right? You say, well, it must just be the energy coming from basically nothingness, right? It's the vacuum because it's not associated with a created or annihilated, photon. So for that reason, we call it the vacuum energy. Okay. And to understand it, like I said, you need to go to a quantum field theory. Quantum field theory to understand, or at least understand how to deal with it, right? But one way that we do deal with it, it comes from Feynman, Richard Feynman, and his basic statement was, just forget about it, right? Actually, he was from Queens, so he would say, forget about it, something like that. But the point is, like we were talking about the other day with the fermions, in the lab or in a real setting, we can't measure the absolute 0 point of energy, right? All we can measure are basically energy differences, okay? And so his thing was, just forget about it because we can never measure that absolute. We can never measure vacuum energy, right? We can't measure the energy of nothing, right? So even though the theory's given us an infinity, we forget about it because it doesn't make a difference to us, okay? And we'll see how Dirac interpreted it. This will pop up when we study relativistic quantum particles. The same issue will pop up. Yeah.
So I kind of got lost. Can you go up to the expression where the one was?
Mm-hmm.
So if that is h, would it be possible to integrate after over k afterwards? Like if we take to find the energy, we take a state with h in between.
Mm-hmm.
If the state didn't have any high k terms, would we just not have to integrate over all of k? Because it'd be zero.
No, but we still have to integrate over all k. Yeah.
It just wouldn't give you zero if it didn't have any high k states.
Well, you have to include all the states. Does that make sense? You have to think about it. It's a little tricky, and it's something that has it takes a. You don't really. I don't think you ever really fully understand it, but it's something that you just accept that it's coming out of the math, and if you take quantum field theory, you'll address it, and you'll spend half the semester talking about it, right, and how to deal with these cases. Okay. But it's basically just because it's not attached to any A and A daggers, it's just the energy of nothingness, of the vacuum. Okay. And then you learn in quantum field theory that it's the energy of particles popping in and, popping out of existence and then annihilating each other, right? So they violate the uncertainty principle for a short amount of time, but there's infinite number of ways that this can happen, and it's always happening, right? So it makes a contribution to the total energy of our universe, basically. Okay. But the way that you deal with it, there's a systematic way that you deal with it. It's called renormalization. Okay. And you'll get to that when you take quantum field theory. But it's interesting that there are actually observable consequences to this. Okay. And it's called the, Casimir effect. All right, so the Casimir effect is where they try to measure. I don't remember what they're trying to measure. They're basically trying to measure the vacuum energy. So go look up the Casimir effect, and you'll see that this vacuum energy does have an observable effect. Okay, on this through this Casimir effect. Okay, so we got to go. So they're outside. But next time, I think we'll start talking about relativistic quantum mechanics. Okay. All right. See you guys Wednesday.